Hello? Okay, it's working.
Yeah. Okay. Yep. Welcome, everybody. First, I would like to remind you that this evening we will have the coding competition, the Google Code Jam. It will be held here at 9 in the evening, of course. Actually, I think it will be in Pizza Margherita. The training room. No training room, but I don't know, workshop room. Pizza Margherita. Okay, that's it. Also, we already have all the files, all the videos from yesterday. They are on files.ep, which stands for EuroPython. Files.ep. If you are connected to the network here, you can simply type that address and you can download them. Okay, so here we are with Leonardo Almeida, which works for Nexedi, which works for Nexedi on the IRP5 platform software, and yeah, he will show us how to take X-rays of our software. Thank you, Leonardo.
Hi. So, debugging is so much fun, isn't it? Debugging performance is even more fun. And it's even more fun when it's the client that's complaining, but when you look at the system, it's not slow for you. How many of you had this situation? Good. So, what do we do to deal with this, which is apparently very common? First, we do prevention. We try to make our software not be slow. And for really important production systems, this usually involves, after all you've done your programming and your debugging and make sure that all your little pieces run as fast as you think they should run, you should do a functional performance test where you simulate the actual use of your system with as many simultaneous users as you agreed in the SLA with your client. Everybody does that, right? Right. 2 people, that's better. So at Nexedi, we always do that, and we use a system based on Mechanize, which simulates access to a browser. Go to this page, click this button, fill this form, and we do that. We simulate the whole script of users performing the functions of that are expected of the site, and we release a bunch of these in parallel with time for taking a coffee and going to the bathroom, all this in the script, so that it simulates a real use case with as many parallel users as you do on as it's to be expected by the SLA agreement with your client. You do that before putting your system in production, right? So, of course, things never work exactly as you planned. There's always something there hidden, some performance problem in your software that is hidden. So what is the usual answer to that? We usually wait for the angry mob with their pitchforks to complain to us, the system is slow. And what we usually tell them when they come like this, we tell them, well, can you explain to us what you did to make the system slow? That usually doesn't work all that well. Sometimes it does. Sometimes the client can tell exactly what you did. Most of the times it doesn't. And the other thing we do is we do proactive monitoring. We'd put some logs and stuff to make sure that the system is behaving correctly. Specifically in the case of web requests, we parse access logs from our favorite web server to make sure that the timed requests are in the good range, and when they are not, we check the URLs that they are accessing to see if they are fast enough. But many times, even if you get a hit from the log saying, oh, this URL was slow, you go there, and it's not slow for you. But in case the client was nice enough to you and gave you reproduction instructions, what you usually do, you use a profiling instruction, or there's the famous one in Python, which is cprofile. If the thing you're trying to profile is already slow, cprofile will make it a lot slower. And so something that was taking a few minutes will take like half an hour until it finish running. And the end result will be a table full of numbers. And you don't know what to do with these numbers. And every time I need to use cprofile, I have to read the documentation all over again. And after 2 hours of divination, I finally understand what to do. And then I see, yes, there's this function that's called so many times, and it's taking so long. But is it taking so long every time it's called? Is it taking so long because it's called so many times? And that's the problem with cprofile. It only shows the calls. It doesn't show how the thing is being called. And in the middle of all the statistics, you can tell which of those calls were actually slow. You just have an average. And it's very difficult to see who called it and why. There is a slightly different thing that I discovered very recently, so I had to add a slide about it. It's called StatProfile. You can download it from PyPy. I'll show the reference at the end. And it behaves a little bit better. Instead of tracing the calls, it traces the lines. And it basically gives you a statistic. It samples the execution of your function and provides you statistics on which lines were the most lines present during the execution, during the samples, at the samples that StatProfile took. This is better, it's more relevant. It doesn't slow down your system, almost. But the problem is it still doesn't tell you the whole story, what's actually happening to you. So it will show you that some lines are slow, but those lines might not be slow all the time or for all the situations. In systems with databases, and if you have an inefficient database, you will frequently see the line that accesses the database there. But which of the queries was executing when this database access happened? You don't have that information. If you don't have reproduction instructions, then it's even more fun. You would never put profile in production to simply run while the system is running so that you can gather statistics of where the hotspot is, because that will basically make your performance problem even worse. So what we do, we sprinkle timing calls, start time, end time, log, what was it doing, a few variables, and, well, it's happening in the production. We have to do it on the production system, right? And then if you have a really retentive sysadmin, you have it getting into fights about downtime and maintenance because you have to restart the system. So that's not fun at all. In Zope, which is I have the most experience working with, we have something called Deadlock Debugger, which helps you when the system is slow right now, because it gives you a snapshot of what the system is doing with all the stack traces of what all threads are doing right now. So first, let me talk a little bit about Zope so that I can explain Deadlock Debugger and the interesting technique it uses. Zope uses the worker model. It launches one thread that keeps listening to the socket, and a few other worker threads that when the listening thread parses the incoming request, it handles it to one of the worker threads. The worker thread go do its work and return a result. In Zope specifically, what these worker threads do is they turn your HTTP request into a method call, like that. Document method foo equals bar, which is very convenient for development. Zope, as most of you know, is the granddaddy of web frameworks in the Python world. For a long time, Zope was the only thing except writing CGI scripts. And it was way ahead of its time, and now people think it's so slow, so boring, lots of stuff, but lots of people still do many heavyweight applications with it. And all these objects for which Zope translates URLs into method calls are stored usually in an object-oriented database called ZODB, which happens to be clusterable. One of these clustering solutions is Neo, also called Neopod, which is developed by Nextd, my company, and I have to mention it because after all I'm being sponsored by my company to be here. So, what does deadlock debugger do? In Python it does like that. There's this little call called syscurrentFrames. Deadlock debugger runs this piece of code, actually this is a simplified version, right from the listening thread. So even if your system is completely blocked with all the worker threads busy, heavily busy doing something, there's a special URL that triggers the deadlock debugger, and it shows you what all the threads are doing. And because it's responding directly from inside the listening thread, even if all your system is crawling, it will still give you an immediate and useful answer. I'll even show it to you. So here's the output of deadlock debugger when the system is doing nothing. Let me enhance a little bit for you. So it shows you some threads. They're basically stuck inside the publisher, the object publisher of Zope, waiting for things to happen. And when you go into some URL, you don't need to pay attention to what's happening on the screen, you just need to know that I'm asking for it to do something that's really heavy. You can see that it's doing something heavy. And then I go here and reload. You can see that there are still some worker threads waiting, and a big one here, which is doing its thing. So, and you can see that this screen showed really fast. Deadlock debugger shows you instantly what the system is doing right now. So if you happen to be lucky enough that the client is complaining to you and the system is low right now, and you have this installed, Deadlock debugger can show you what the system is doing at that moment, which is fantastic. Nextd has solved quite a few problems this way. There was a problem with the translation subsystem that we use that had a setting for automatically creating new base translations without the equivalent translation into each language whenever a new message had arrived. And the system was creating new messages because it was calculating new messages whenever something happened, and these new messages had as input the title of new content that the client was adding in the system. So it was trying to translate all the content of the client for some stupid reason. And that meant that the translation object was constantly circulating back and forth between the database. So we could see very clearly in the traceback that there was a call going to the database, and it was coming from the translation subsystem. That was wonderful. So we knew that something in the translation, it could go into the translation subsystem, put some information on why it was doing that. We could also see why it was trying to translate, because it would be upper in the stack, the reason why what it was trying to translate. So, Deadlock debugger is excellent, but it only works if your system is low right in front of you. And what is this? You can see back here, I put it in red, it loops through the syscurrentFrames, and for each frame, it prints the stack trace into a string IO, which is a virtual file, and then returns that to the client, to the browser. So what is it? SyscurrentFrames returns a dictionary. It's now part of the sys module. Before that, back in version 2.4, there was a C-compiled extension that exposed the same information called thread frame. I must mention it here because for all that I don't remember the guy who created it, but it was very important in the Zope community when we discovered this. And it returns a dictionary with the identifier of each thread and the tip of the stack frame for each thread. And then you take another function in the standard library called format traceback or print stack in this case, and you give it this frame and it formats a nice trace. And I've just disconnected my microphone. I move my hands a lot. I'm called Leonardo for a reason. And so I should probably, even though I'm Brazilian, so I should probably get these wires out of the way. So it returns a dictionary with all the threads. That's all the threads. And the stack trace, and the tip of the stack frame of the stack for each of those frames. This is very interesting. You can do a lot of interesting stuff with each of those frames. A stack frame, the tip of which we get out of syscurrent frames, each one of those contain the file name, the line number, and the pointer to the previous frames. So that's why it's a stack. The bottom frame doesn't point to anywhere. Points to none, actually. But it has the dictionary of locals and globals. You can actually evaluate Python expressions in the context of all those stack frames. So that's actually quite powerful. You can introspect what's happening in them. You can take information out of them, out of all the stack frames. So deadlock debugger gives you an instant snapshot. That I showed it to you on the other screen. It shows each thread and the stack trace for each thread. It's good for when the system is low right now, as I explained before. And of course, going back to what we were saying, besides waiting for the angry clients with their pitchforks, you can also do proactive monitoring. Most of it is parsing HTTP server logs, or you can put something in your parsing your MySQL logs or your database logs to see which kinds of SQL requests were slow, for example. But that's still not enough info. In the HTTP request case, you could get many false positives because, as I showed to you in the case of Zope, if you have wasted all your worker threads, if they are all busy doing something, then all subsequent requests are going to be slow. So the access log is not going to tell you much except, hey, this bunch of stuff is slow. You might try to see which one of those started being slow first, but it could be a cascade effect, like you had a peak of client access at some point, and in the middle of that you got a slow request, and the system never got out of that state for a long time. So really not much information. And you have matkit, which was now absorbed into Percona, which gives you the whole SQL the query that was slow, including the information of what's the structure of the table, what indexes are defined for that table. That's usually very interesting because you can optimize those SQL accesses by changing indexes, perhaps. But it doesn't tell you who was the idiot in the application code who called this slow query function, so that perhaps you can actually do a smarter call. You can many times divine who did that SQL call by the shape of the SQL query, but sometimes you don't. So can we do better than that? What if we could run deadlock debugger continuously? Because, and this is was actually common in the Zope community, whenever the client would complain that the system was slow, we would tell the client, please hit the deadlock debugger from your screen right now, so that he could mail it to us, and we would analyze it, and we try to train the clients to be like our little monkey pressing buttons to dump the queries for us. That's not really client-friendly, but this is actually the best we could hope to do. So can we do better? What if we put deadlock debugger inside the actual Zope publication mechanism and monitor all the incoming requests, but dump traces of only the ones that were slow? And we could also be smarter, and in the process of dumping those traces, like I said, there's local variables available for each of those traces, we could actually extract more information out of it, like what was the URL, what was the user accessing. You could basically pull any information from any frame that you want. You just need to identify the frame and pull the variable from inside it. That's why I built long request logger. It dumps into a log file this information for each request that is low. The following request with this URL and these variables running on thread with ID Y is running for t seconds, and then an information from the request, not only the URL, but form values and the authenticated user and things like that, and the stack trace. And again, 2 seconds after that, if we configure the system for 2 seconds, you get the same information, but now at a point in the future. And what did this help us with? I have a client which I'm not supposed to tell what it does and who it is, so I will pretend it's a t-shirt printing company. Actually, it does something else, but let's pretend it prints t-shirts. And we, obviously, this is our main product. We install EuroPy5 for this client. We have a maintenance contract with them. EuroPy5, and now is the part where I do the advertisement, is a complete ERP solution with MRP, CRM, a bunch of 3-letter acronyms that business people like. Accounting, controlling business processes, causing things to happen because some other things have happened, like an order comes in, so you need to produce something else, so it automatically creates the sale packing list from the sale order, and then the invoice from the sale packing list, and make sure that the people who need to see the information to produce all these things or to move all these things around can see them at the moment and notify the system that they have finished doing it. All this stuff. And it's ZOAP-based, but has a MySQL index to locate the objects quickly. And it also has a background activity system which takes care of, among other things, to index these objects that are stored in the object database into MySQL system so that the operations are fast and don't have to wait for indexing before returning the interface to the system so that the system is more responsive. And we rely heavily on this background activity system to do things that would be slow if they were done synchronously. And the fun part is that the operators complain that from time to time there will be peaks of horrible performance, and they would be very random, never on the same place, never on the same URL twice. And these peaks of terrible performance happened at moments of high volume where the performance was already not that okay. But most of the time, the not okay performance was acceptable, except that some places, some screens that a user visited were horribly slow and take like minutes to show up. It was impossible to get the client to provide meaningful reproduction instructions for it. So at Nextd we created long request logger. It was designed by Julien, Sébastien, and me, and I implemented pretty much all of it. And it shows which requests were slow, why exactly they were slow, because of the traceback and the extra information we extract from the stack frames. And it also helps us to see which is the right spot to add optimizations. So let me explain a little bit about this client. In EuroPy5 we have a sales order, which contains information like the source, which is the supplier, the destination, which is usually the client, but could be someone else that the client bought for, so there's a whole bunch of complicated situations. All the global discount and taxes that apply to the whole order, and a collection of sale order lines. A sale order line is not exactly one item. It's more like a description of a collection of items that have the same characteristics. Like in the case of our t-shirt buying company, the company could be buying 10 blue t-shirts with printed EuroPython 2010. So you have these characteristics. A sale order line represents one item of these, and then you can have another line which is 10 black T-shirts with EuroPython printed on it. So for each different combinations of variations of a product, you would have a sale order line. And the sale order line is responsible for displaying the global price, the price that is calculated by collecting all the prices from all the lines and applying the global discounts and taxes. Each sale order line, as I said, can have a resource, which is usually a product type or something that we are selling. It could also be a service. But basically anything that you want to put in as an identifiable thing that the client is acquiring. It could have resource variations. In the case of the T-shirt printing company, it would have different color for the T-shirt, the number of colors for the print, the priority if this was an urgent order or not, and a message or the text or graphics or whatever that's going to be printed. Of these, the color of the T-shirt does not influence the price. If it's not a special color, perhaps it does. But the number of print colors does influence the price. And of course, the priority influences the price. And each one of these is calculated separately for each order line. And not all variations influence the price. And you have the price of the resource is then multiplied by the quantity of the T-shirts. And the price of the resource is configured in another entity in EuroPy5, which is the price list. You can have generic price lists that don't have criteria for applying to anyone, so they apply to everyone if they are valid. And you can have customer-specific price lists. And each price list is a matrix, is a multidimensional matrix of all the possible variations. And for each variation, a combination of variations, and for each variation, it specifies if that thing causes it to have a fixed price, or if it increments the base price by a fixed amount, or if it increments the base price by a variable amount, or if it's a discount, it's the same thing but decrementing it. So you have all these combinations of possibilities just for calculating price. So in the end, each cell of these price list matrices is a predicate in the system. It has a condition that can apply or not to a cell. And we pile up all these, for each sale order line, we pile up all the pricing predicate cells, order them by priority, and select either the fixed price or the variation, the fixed variation or the proportional variation for each one of those according to their priority. You can see it's a very complicated calculation. You don't have to remember all that. You just have to remember it's complicated. So each sale order line price is calculated on demand. When the order gets into the system, it's only identified as, oh, it's this kind of T-shirt with these variations, and the price is empty. So as soon as this order gets into the system, as soon as each order line gets into the system, it is re-indexed by the indexing solution, which puts information in the MySQL catalog. And as a side effect, it calculates the price. So most of the time, by the time the client actually looks at the order, the sale, all the sale order lines have the price. And if it doesn't, the fact that they are looking at the price automatically triggers the calculation of the price. And the price is then stored in the sale order line, so that for two reasons. One is so that it doesn't have to be calculated anymore, and two, so that an accountant or someone or a sales guy with enough permissions, or even a manager, could go there and manually change the price of that sale order line. So it's a very flexible system. And if you go there and have permission to do that and erase the price from within the sale order line, the sale order line is recalculated almost immediately. because you're looking at it, or if for some scripted reason that price is calculated, then it will be, the price is removed, then it will be recalculated by a background reindexing activity. Wow. So I have to run. So what does long request logger do? It wraps the original publishing mechanism in ZOP. You can see that the wrapper function, it instantiates the monitor, wraps the original call, calls the original call, and returns the result, and finally it stops the monitor. And we publish the ZOP, the ZOP default publishing mechanism to do that. The monitor is a thread object that is started as soon as the other thread is started, and from time to time, while the other thread has not finished, it will call the dumper to dump information about the thread. So here you have a definition of the waiting is basically returns true or false if the original thread has called stop or not. And the way we do that is by a pipe that we share between the two threads, because this we discovered is the most efficient mechanism. If you use a semaphore and you are in a virtualized environment, VMware, depending on the host CPU, doesn't like very much doing locks. So we use the pipe, and that was a lot better. The dumper will receive as parameter the thread, the original thread ID, and will print the stack. And also, while printing the stack, if it localizes a request variable in one of those frames, it will capture information about those frames. There's more stuff in the dumper class, which I'll not show because they're just formatting instructions. So why does it work? Because it provides sampling profiling, and because it's from time to time, every, for example, 2 seconds, hitting on printing the stack dump, it will obviously show exactly what is low. If you're randomly shooting in a certain direction and there's a big target passing in the middle of a bunch of small targets, your chance is high that you're going to hit the big target. So it's pure probability. What is showing up in the traceback is actually what is low. And the sequence of tracebacks that we get from the moment we decide that this thread is going too slow till the end of the thread tells you exactly what's happening. It's starting to do this, and then it goes to do that, and then it goes to do that. And you can leave this running on the client, and it will capture even the most unreproducible slowness that the client experiences, because it's running continuously, and it's automatically triggered whenever the thread is low. And we don't need to rely on the client. We can actually see these low threads and act on them before the client even calls us complaining. So how do we know what to optimize? Let me show you the output of this log very quickly. So you see there's a lot of information. Pay attention to this first line here. It will show the thread ID. This is a timestamp on when it was started. It will tell you when, for how long this thread has been running, and which URL it is accessing, plus all other information we can fish out from the request, including which was the authenticated user, what was the URL it was accessing, and other information that we currently collect. This was captured because we have a configuration that starts dumping at 8 seconds, and when the thread lasts more than 8 seconds before returning to the client, and we dump at every 2 seconds. So if we compare let me go back here. Going back here, so we have the request information, and back here we have the traceback. It's a long piece of information. but it tells you what the client, what the request was doing at that moment. And you have a bunch of those in the log file, which means that you can do comparisons. This is a three-way comparison of the stack traces at three consecutive dumps. I will show you over here. Pay attention to the first line. First we see here that it was running for 20 seconds. The people back there can read it or not? And here it was running for 22 seconds, and here for 24 seconds. So we are seeing this in MELD, which is a wonderful file comparison tool, written in Python, by the way. And we can see that the first part of the stack trace is all the same for all the three stack traces. Then they begin to change. And the last part of the stack trace is completely different. So what does this show you? Is that we have a cold part here up top and a hot part here up top, which is constantly spinning. And so what is it that we have to optimize? What is burning us time? Is exactly this part here in the middle. So that's how you analyze what's making you slow, and you can pinpoint exactly where you should go to make your system go fast. You don't have to guess. It's just the part between the hot and the cold. You go there and you analyze your system, you analyze your business rules, you analyze how you can cache things or maybe not do certain calculations because they were done before, and there you go. So what is the challenge of this solution? The problem is that, especially if you have a system that is frequently slow, you're going to have a huge file. And you have many things that go slow, and you have to focus on what you do first, which is why on that dump you had that very long line which had the initial timestamp, the number of seconds, and the URL, because that makes grabbing faster, because right now the only user interface we have for that is grep and your favorite text editor. And since it's a single log file for all the stack traces, you will have request X, request Y, request X, request Y, request X, request Y. But you can jump from one of them to the other by searching back and forward between the same thread ID and the same request. And you can check that you're still on track because the time will be decreasing as you go up and will be increasing as you go down. If you find the same thread ID with a time that has decreased while you were going down, it means it's a new request. Same thing as if you go up, you eventually hit the 8-second mark, which was what we configured in the system, and that was your first call. And before that, the same thread ID will have a different request with a time that's bigger than 8 seconds. So you can find all the tracebacks that your requests were doing, but we don't have an interface for that yet. So it's kind of very manual work. So that's the current challenges. Future improvements. It would be nice if we could make a reusable library out of it, because the technique of launching a thread to monitor another thread is reusable for anything that has threads doing work. So it would be nice if this was not constrained to the ZOP world. And also some helpers for analyzing which URLs were the most slow, to be able to search and sort, to move between tracebacks faster without you having to copy them into a file comparison tool. We could also add more information extraction for frames, or put a little pluggable system that maps a dictionary from a function. If I hit this function, please extract this information. And collect that. We could also, instead of dumping this to a text file, dump this to, I don't know, MongoDB, for example. Then you could do better statistics, have a better user interface, and also add some ignore sets to say that I know these URLs are going to be slow. They're only triggered by the background execution mechanism, so I don't need to worry about them. Don't print them to me. I know they're slow. And we have a few open questions. What is the true performance impact of this? We are running this on production, and the only time we had a problem was when we discovered that VMware doesn't like locks. And then we switched to using pipes for communicating between the monitoring thread and the original thread when it wants to tell it to stop. But if we redo, but this you saw, I configured it for 8 seconds for starting to complain it's slow and 2 seconds to dump every time. This is horrible. If this is like a startup company trying to find clients, if you're trying to build the next Twitter and the user is waiting 8 seconds, you're never getting off the ground. We can get away with this because the ERP system and our direct customer is not the direct operator, it's the poor guys in operation that have to complain about the system being slow. Of course, we are constantly improving working to improve that, and every month we go take the biggest problem out of the long request log, work on it, and then the client is very happy that the system is faster. But if we want to do this for a very, very high performance site, how short can we make the interval between dumps before the dumping system starts interfering with the original threads? Do we start disputing the big interpreter lock between the monitoring thread and the original thread if we do that? Can we improve that by having a single monitoring thread instead of launching one thread per monitored thread? These are the things that we can improve for the future. And that's it. Here's the references. There's this very interesting Stack Overflow question which has nothing to do with Python. It's about debugging C++, but the guy does all the kind of theorizing about how doing this kind of stack profiling by sampling the stack trace and preserving the stack trace instead of throwing it away and keeping just the statistics is actually a much more useful tool to pinpoint the slow parts in your code than the current debuggers are doing. Of course, there's the reference to StatProf, which has resurfaced. And Nexity, my company, and the EuroPython, the solution that we provide. This is my Twitter, Leo Rochael, which I've never posted at. I guess this means that I need to start looking at it more. And my business and personal email addresses. And thank you very much. And it's open for questions.
Are there any questions?
Hi. You mentioned on a previous slide that the stack, I forget the name of the function, where you get the stack information.
Current frames, syscurrent frames.
Yes, that you, some part of that is related to just to Python 2.4. Am I?
Right. In Python 2.4, that function was not exposed yet. But there was an installable module, which was a compiled C extension, that provided the exact same information. That module became so kind of popular that the Python folks decided it was better to just expose this directly.
Okay, thank you.
And it exists in Python 3. And it behaves exactly the same. So this exact same technique works on Python 3.
Hi, Leo.
Hi.
I'm not so sure how to phrase this without sounding too much like a smartass, but there's actually another package coming from the Plone or more like Plone community. It's called Comatos Poke, which does more or less exactly the same thing. Was there any reason why did you not know about this, or was there any reason why you didn't like it? And
I've heard about it. I must confess I haven't looked at it closely. This tool I developed in one day and another day to write tests and package it. And I know quite a few people in the Plone community who uses this tool, so I don't know if they also have not compared. My friend Erico Andre is here, and I'd like to mention the case that he sent to me that he also solved with long request log, in which he discovered that the backup solution was hogging out the bandwidth out of the network interface, but this happened only sometime, and only one person complained about it, and only one node of a cluster of nodes. So it was...
No, I was just wondering, I mean, the other package is probably not that well known because it was also put together in a short time. It's based on Deadlock Debugger as well. And I think the only difference that I could make out basically is that it actually collects the traces over time and then only sends them or like only prints them out at the end of the request. And if you use that together with the mailing logger, that makes it quite nice because you can send, like we used to send emails to a Gmail list basically where you can search for stuff. And,
Okay, good to know.
And by
I'll
now
take a
it
look.
also works with a Pyramid, by the way, on a whiskey stack, so that makes it a little more independent from SOAP.
So if it works with Pyramid, it's probably based on WSGI or not?
Yeah.
So yeah, that's the thing. Christian Tiny who had a talk the other day that this tool is actually a WSGI tool, and there's a lot of people not using WSGI, ZOAP with WSGI yet, I guess.
Komato's poke is based on ZOAP and Plone, but and I'm not sure if it's actually the same package that supports it or if it's a fork, but we are using it on Pyramid as well by now.
Okay.
A colleague of mine set it up, so I don't know exactly, but I could check it out.
Okay, good to know. In any case, the main point of my talk is not to make not to advertise long request logger, but to actually advertise this technique for dumping, which I think is more useful. Yeah. Okay.
Could you repeat the name of that other tool that works with WSGI?
Comatose? Just Comatose. Ah, Comatose poke. Okay, Comatose poke. Anyone else?
Does this technique work with gEvent and eventlet? Does the sys current frame still return you useful information?
I have no idea, but I will hazard a guess. This function generically returns a dictionary mapping thread IDs to the tip of the stack frame. In Greenlet environment, suppose you have only one thread because all your multi-processing is being done by eventlets. Then you only have one thread. This dictionary will have only one key and only one value, and this value will be the tip of the stack frame of whatever is executing. So I guess you would see the main execution thread and not see any other greenlets because they would be stashed away. Because if you think about it, we call it a stack frames because we see it piled on, but in reality it's a linked list. We have the tip of the frame and a pointer to the back frames all the way to the main function, for example, or the main module that is executing, and this guy points to none. So this is a linked list. You can very easily make a linked list and turn it into a tree. And I suppose this is what the greenlets do. They create kind of chains of stacks that represent frozen executions, and they stash them away somewhere. And then when it's time, when you invoke the appropriate API, they go back to those. So looking at this tool, you'll see a single thread in the main thing that is executing right now. So it will still be useful, but it will not show you all the greenlets. It will show you only the main execution. That's what I speculated. I don't actually know this for sure. Okay. Any other question? Nope. Okay. Then thank you very much.
Thank you very much, Leonardo.